Welcome everyone to our Distinguished Lectures series in the Allen School. So Zach and I, who've been organizing the lecture series this quarter, next quarter, really thrilled to host Brad Calder to give our lecture this time today. So Brad has had a very distinguished career in academia and in industry. So Brad was a professor at UCSD. And there he actually graduated to people that I really like or at least to people that I really like in the architecture community, Tim Sherwood and Satish. He's accomplished producing great students. And he left academia exactly at the right time when the cloud systems were starting. So Brad went to Microsoft and helped, ramp up Azure there, and then moved to Google to build cloud systems at Google. So, it's very rare that we get to hear from someone who built two major cloud systems and timed their transition from academia to industry so perfectly. Brad, thank you very much again for giving a lecture to us, and we very much looking forward to hearing from you.
All right, thanks for the introduction. I also want to give a thanks out because I did my undergraduate at University of Washington, and so I have very fond memories being a student there. It was an amazing time in my life, and very thankful to the faculty that invested in me while I was there. Just want to call out thanks to some of the faculty like Hank Levy, Larry Russo, Paul Beam, and Lazowska, and many more who helped in my education and shaped my early years. So I wish I could be there in person, but I'll have to settle with this virtual visit. So thanks for having me. My talk today is about the cloud. Cloud has progressed significantly in the past handful of years, and businesses are needing and demanding the ability to connect to their customers around the world for business critical applications 24/7. This requires creating and managing five nines applications. So given the importance of five nines applications, I want to spend today talking about how we do this at Google and how you can do this in Google Cloud. So five nines means creating and managing applications that are down for less than 5 minutes a year. So applications are expected to always be on and always be available. So, and achieving five nines is a complex and demanding, and there are several fundamental principles that need to be met. And I'll touch on some of these during the talk, and I don't have time to go over all that's listed here, but I want to highlight the main point at the bottom, which is that detection and mitigation of issues needs to be automated to have any chance of achieving five nines. Any outage that involves humans to solve it will take over 20 minutes to resolve, and 20 minutes of downtime can be a disaster for a company and their users. So I want to start off by giving insight into how Google builds for five nines, and then I'll dive into how to approach this for Google Cloud. At Google, we have 9 applications, each with over 1 billion users worldwide wanting access to search, YouTube, docs, and photos. And each one of these is a global application built with microservice architecture consisting of hundreds of microservices. And there are 4 key parts for how Google achieves high available applications. These are managing and scaling microservices, being able to control and steer traffic at a global level, and having application data that's durable and always available around the world. And finally, we assume everything that can go wrong will go wrong, so the application layer needs significant investment in the principles of high availability, as I indicated on the prior slide. So how do we build applications with microservices at Google? All of our microservices are run on Borg, which is Google's distributed task scheduler. And the microservices leverage the common building blocks and tooling shown here to produce globally operational services that are secure. So here's an example of a Google service made out of microservices where each box represents a microservice and the arrows show RPC dependencies between them. And this is a highly available service at Google where every layer of the microservice is architected for resiliency. So as you can see, devising an application out of lots of microservices looks complex. And for these large applications with thousands of microservices, there needs to be tooling and support to understand, manage, and operate these services at scale. So how do you manage and reason about hundreds of microservices for your application? Well, we've learned a lot over the years building microservices at Google, and we've shared these learnings as open source and cloud products as shown here. Now, 3 parts of this include, first, the importance of having API contracts between microservices using protocol buffers. This is to specify the formal interactions between microservices who tend to be owned by separate teams in a company. And the protocol buffers also ensure backwards and forwards compatibility between these microservices. And second is having a container orchestration system for running and managing your containers, which we provide with Kubernetes. And third is the learnings we have around microservices, which motivate us to provide Istio. This is our open service mesh that provides network support for enabling service discovery, telemetry, and connecting your microservices together. And I'll be diving into using a service mesh later in this talk. So across these building blocks, you have a set of base technologies needed to build and manage your microservices in the cloud. Now, a key part of being able to run a global application is having regions around the world in which to run your microservices. Also important is having a global network to connect everything together and to steer traffic globally for those microservices. And at Google, we have 24 regions around the world in which to run your microservices and 144 edge locations in which to enter our global network. And in addition to this, we have over 3,000 edge locations for delivering content over our edge network, which delivers our content for YouTube. And we're opening up the full reach of our edge to our cloud CDN customers in this coming year. So our global network and region footprint allows us to run microservices in many regions around the world in what we call N+2, where there's N regions needed to run the service with a little extra overhead. And then there's +1 region for maintenance and another +1 region for failures, where we can completely drain traffic out of a region and be just fine. And over the years, we've developed a set of traffic management tools ranging from global load balancing, intelligent autoscaling, DOS protection, and routing traffic around network partitions. And this even includes routing around network issues created by non-anticipated attacks, events like shark attacks. So you can see this shark nom-nomming on our undersea cable, trying its hardest to partition our network, but we're protected with redundant routes. So just as important as running your microservices around the world and keeping the traffic flowing is also having access to your application data at all times. So at Google, this is provided by Spanner, BlobStore, and our content delivery network. And these are all provided also as Google Cloud Services. Now, in addition, Google also relies heavily on petabyte scale data analytics, streaming data processing, and message delivery systems, which are also provided for both Google and cloud products. And finally, I want to mention that even with all of this infrastructure and building blocks just described, the application needs significant investment for 5 nines. This includes defensive depth, graceful degradation, traffic management tools to protect your application, experiments, and much, much more. And I'll touch more on this towards the end of the talk. Now that I've talked through at a high level the building blocks used at Google for creating available applications, I want to focus on what we do at Google for Google Cloud to provide 5 nines support. Now I'm going to focus on 5 areas for the rest of the talk. I'm going to first start off with data and how we manage that. Then focus on scaling and managing microservices with load balancing, auto-scaling, and using a service mesh. And then I'll finish up with how traffic is routed and controlled when there are issues. So let me start off with data. A global 5 nines application needs a highly available database, and for both Google and Google Cloud, we use Spanner. Spanner provides strong consistency with SQL ACID transactions that automatically scales and shards your database on your partition key. It is globally distributed, and our large applications at Google use it for their highly available data storage and database. So what makes Spanner possible is a combination of our global networking to avoid network partitions and TrueTime, which provides our highly accurate timestamp service powered by atomic clocks. TrueTime is a highly available distributed clock that enables Spanner to reason about the global ordering of events. Cloud Spanner uses TrueTime to implement a distributed timestamp oracle. So this allows each Spanner server to have a local timestamp for multi-version concurrency control without the need for global communication. Okay, go ahead.
Oh yeah, so just like, are you going to talk more about TrueTime later, or should I ask a question about TrueTime now?
I'm not going to talk about TrueTime in more detail later, but go ahead.
Oh yeah, no, just curious. So is the idea then you have a atomic clock per data center or per group of data centers if they're close enough geographically? How do you even think about provisioning atomic clocks as, I guess, as resources, right? So
yeah, I think I don't know the actual details of the deployments off the top of my head, but I do know that we have them spread out across the regions around the world, so that effectively every region has a local timestamp in which it can run off of within a certain amount of error.
Cool, great, thank you. It's a really cool idea.
And so these local timestamps allow Spanner to commit transactions and synchronize copies of the data locally with efficiently without requiring the global communication that I just mentioned. And then there are two typical deployment models for how Spanner is used for a global application. The first is focused on having 3 multi-region Spanner databases for your application. So you have 3 databases, one in Asia, one in US, and one in Europe. And so this is what you can actually get today when using Google Cloud. So you can create these 3 databases, and across these three separate databases, they provide low latency writes and strongly consistent reads, each within their geographic continent locations. So this approach requires the application to partition its data space across these 3 databases. And it's often used for applications where you can do this type of partitioning. So for example, a prime example is if you have a data model that's partitionable by user, where a given user data will be homed in one of these 3 databases closest to the user, where the user geographically resides. So the data is located in that geographic region for efficient access within that continent, even though you can access the data globally, even as folks travel. So this is one example for how Spanner is used to store and access application data around the world. Another example is if you use Cloud Spanner's global deployment, where we have a single database spanning the whole world. In this case, you have 9 replicas across 5 regions around the world, as shown on this map. And then for this database, all the writes are committed to the US and then quickly propagated to Taiwan and Belgium. Then strongly consistent reads are supported globally, which is a key feature of Spanner, though strong consistent reads that are outside the US may require a round trip back to the US leader for freshness. Then of course, in addition, bounded and eventually consistent reads are officially supported everywhere. So, global Spanner is used for application data that needs global consistency, and for data that's potentially not easily partitionable by geographic location. So, and as an example, customers use this for retail inventory and catalog metadata. So Spanner is the cornerstone for how Google and our cloud customers provide highly available data for its applications. And for today's talk, this is all the time I have to talk about the data management. But if you're interested in learning more, there's many more details about Spanner, and including its OSDI paper, as well as more storage information about our storage systems online. Now I'd like to focus on microservices and the load balancing part of building and running a highly available application. When you run your microservices on Google Cloud, the underlying virtual network is provided by Andromeda, which is our cloud software-defined network. For each customer, Andromeda allows all the regions to securely talk to each other, and provides the ability to globally route all your traffic around the world for load balancing and to route to the correct regions for serving your traffic. It basically provides a global VPC for each customer, giving each customer their own private network with their own private address space. So as you build your applications, the microservices are typically built out of VMs or containers placed in N+2 regions around the world and integrated into load balancing and auto-scaling. And I want to first focus on load balancing and why it's so important. So let's take, for example, this game Pokemon Go by Niantic, which runs on Google Cloud. When launching an application, especially a game, it can be very hard to predict how much capacity is needed. The elasticity of the cloud is a perfect fit for having success for a game launch. So shown in this graph here is the target traffic and the worst case traffic, the orange and red lines that the Pokemon team were estimating at launch. But as you can see, the game was a huge hit. And the green line shows the actual traffic that they ended up seeing, which is 50 times plus that load. So at launch time, they used a regional load balancer based upon these estimates, but quickly found that that was overwhelmed by too many clients, DOS attacks, etc. And we worked hand in hand with Niantic so that within a few days, we switched them over from that local regional load balancer to using our global load balancer to meet their scale and address these issues. And let me dive into what our global load balancer provides next. So the global load balancer has a global view of the traffic coming into the Google Edge in terms of requests per second. It knows the microservice endpoint VIP that the traffic is being sent to, and it knows how much RPS microservice compute capacity there is in each region for serving that traffic. Then every few seconds, the global load balancer uses a waterfall algorithm to calculate how much traffic to send to each region, and then it updates our edge network with that programming. So let's go through the waterfall algorithm in more detail. So the first step is that local traffic flows is preferred to flow within a region in which the traffic is coming in to VMs or containers in that microservice within the same region. So let's look at an example here. So assume we have a microservice using our global load balancer, and the load balance points to 3 instances of our microservice running in 3 regions as shown here. One in US, one in Europe, and one in Asia. And we have 100 requests per second coming to the US, 30 requests per second coming to Europe, and 50 requests per second coming to Asia in the blue, red, and green colors. Also shown here is the amount of RPS microservice compute capacity there is in each region for the microservice, shown with the 100 RPS in US, 150 in Europe, and 50 in Asia. So at this point, the global load balancer knows 3 things. It knows 1, the amount of traffic being generated around the world. It's tracking that in real time. It knows the geographic distribution of that traffic, which allows the global load balancer to know the closest region to preferably send that traffic with the lowest latency. It also knows the request per second of compute capacity for the microservice in each region that's available, that's healthy. In this case, the 100, 150, and 50. So given all this, the load balancer programs the Google Edge around the world to send all the traffic locally, since it knows that the local regions can all handle all the traffic. Now, if there's too much traffic to a given region for the global load balancer, we realize this and overflow the traffic to the next geographically close region that has available capacity. So continuing with our example, the traffic in the US, let's say, has picked up to 120 requests per second. And the global load balancer sees this and knows that this region can only handle 100 requests per second. So the load balancer looks to offload the excess 20 RPS to the next closest region with extra capacity, and in this case, it's Europe. So the global load balancer then programs the Google Edge within seconds to split that traffic and to continue serving the traffic efficiently around the world. Now, note, in this example, I'm not using auto-scaling, but I'll show how auto-scaling ties in with load balancing in a bit.
A question on this. How does something like GDPR work into this system?
Yeah, great question. So that has implications in terms of sometimes keeping data local, as well as how long you actually keep your data for example. And for locality reasons, some applications may build their databases or their services so that they actually have this application running in maybe each region that we have available. And then they'll actually keep the data in maybe a spanner database in that region. And if you're doing that, you can actually set it up so that you actually don't have overflow for your traffic for that configuration.
Thanks.
So another example scenario is if a region is unhealthy or having health issues. For example, maybe a rollout was done to the region that is causing the service to crash in that region. The global load balancer will realize through its health checking that this region is unhealthy and redirect traffic to the next closest region and capacity to serve it. So let me take a detour for how health checking works here. So combined with our global load balancer, we have what's called universal health checking. As part of that application, you configure what's called a readiness health check for your backend microservice. This health check indicates that your microservice is healthy and ready to take on traffic. Then this configuration is used by Google Cloud to program Google's internal health checkers in each zone that continuously probe the corresponding ports for your microservice, checking its readiness to serve traffic. Take the example here for myapp.com, where we want to check two different ports, port 80 and port 443, for two microservices A and B. So underneath the covers, the three health checkers shown here independently check both ports, and then they send the result to the Google internal health manager in the same zone shown in the picture. The Google Health Manager then in that zone aggregates the results and makes a corresponding recommendation up to the global load balancer for health of both microservices. So in this example, on the right, the health checks are saying that that for microservice A, all the health checks are green. This means that the microservice A is currently healthy and should be sent traffic. And that gets propagated back up to the load balancer. But for microservice B, there's two health checkers failing, as shown with the yellow lines, and the third one is passing. Well, the health manager sees that over 50% of the health checks are failing, and so it'll tell this to the global load balancer that microservice B is unhealthy and should not be sent traffic in this zone. So this is all aggregated back to the global load balancer that makes decisions about what endpoints are healthy and unhealthy to determine if traffic should be sent back to them or redirected to a different set of backends. Now that you have a little insight into health checking, let's go back to our load balancing example. So where we left off with health checking, if there are unhealthy backends, the global load balancer will realize this through the process I just described, and it will redirect the traffic from the closest region to the closest region with capacity to serve it. So let's continue with our example. So let's say the Asia region has a rollout that causes the region to become unhealthy there. So the health checks will realize this in this example and tell the load balancer. The load balancer will then reassign the traffic to Asia, from Asia to Europe. And it knows that it can do this because it knows how much capacity that the Europe region has, that it has 150. So it knows that Europe can actually take the 30 RPS plus the 50 RPS just fine. Then finally, if there's more global traffic then all the microservice capacity in the globe to serve it, we go into what's called worldwide overload. In this case, the global load balancer calculates an overload factor to evenly distribute the extra incoming load across available regions. So, and typically there's a little bit extra overhead in each region due to the N+2 we talked about earlier. But once traffic goes above the capacity that can be served globally, even above that extra little headroom, it is up to the application to perform graceful degradation and as appropriate to deal with the additional load. That is, unless you can actually get more capacity in those regions, which is where auto scaling kicks in. So continuing with our example, in this example, we have worldwide overload for the load balancer, where we see now a big spike in Europe with 260 RPS coming in. And the load balancer then applies what's called an overload ratio to each of the region's microservices shown at the bottom of the slide. Okay, it then assigns, based upon that overload ratio, the corresponding traffic assignments to each region in the US, Europe, and Asia. And again, in this example, we're not using auto scaling. So this motivates the importance of using auto scaling to deal with these types of spikes and failures, and let's talk about that next. So we provide auto scaling integrated with global load balancing for VMs a day with containers coming in 2021. And our autoscaler knows how much RPS a given microservice in a zone and region can handle. In addition, it is told by the global load balancer how much traffic the load balancer would prefer to assign to that region based upon the waterfall algorithm that we just described. So then our autoscaling with this information can then grow the capacity in that region in one step to the size that the load balancer is asking for, reducing the time it takes to grow a region or zone to serve the traffic that wants to be served locally. So let's go through a more simpler example here to demonstrate this. So let's assume we have two regions, A and B, where our global edge sees 10 requests coming in for region A and 10 requests coming in region B, and it wants to send that traffic locally. And each of the two regions has 30 RPS microservice capacity within those two regions, A and B. Now let's assume that there's a traffic spike of 50 RPS that the global load balancer would prefer to send to region A. But region A only has 30 RPS capacity for its microservice. So as described earlier with the waterfall algorithm, the load balancer will realize this and offload 20 RPS and send that to the region B. Okay. At the same time, it also tells the autoscaler in region A that it would prefer to send 50 RPS to it. The autoscaler sees this and says, okay, I will autoscale in one step from 30 RPS to 60 RPS. And note that this is higher than the desired 50 RPS because it actually has a little extra headroom for the microservice in the region. So, and you can configure when you set up your autoscaler how much extra headroom you would want when the autoscaler configures itself and grows capacity. Then when this autoscaling is complete, the autoscaler informs the global load balancer how much available microservice capacity there is now in region A, which is now 60. And then the global load balancer programs the edge to direct the traffic with a new capacity allocation, so it now can serve that 50 RPS locally in region A. So as you can see, having load balancing and health checking integrated with autoscaling is critical to keep the application serving even in the face of traffic changes, spikes, region failures, and preventing worldwide overload. So now I'd like to talk about service meshes. So we just talked about how traffic gets routed and load balanced from the public internet to your microservices in the front end, but the same type of support is needed across the hundreds of microservices that make up your application. And that's where a service mesh comes in. At Google, we took our learnings from managing hundreds of microservices for an application and proposed the open source service mesh, Istio. And since then, a number of service meshes have really exploded over the past 3 years. So what is a service mesh? Think of a service mesh as a software-defined networking for services. You take your application, remove all the networking code from it, and move it to a service proxy. Now, you need a way to configure and control and apply policy to these proxies and manage them. And that's provided by the service mesh control plane. So a service mesh is especially important as the service grows to hundreds of microservices in order to understand and manage all the complexity as shown in the microservice architecture I showed you for Google at the beginning of the talk. Now, let's take a closer look at a service mesh. In this architecture, you can see that a proxy is attached to the microservice binary. This is a sidecar proxy. And it abstracts out the outbound and inbound features shown here and manages this complexity across all of your microservices while providing traffic control, visibility, security, and policy enforcement. Now, there are 3 options right now for the service mesh data plane. So let's go through those. First is a standalone service proxy called a gateway that can be inserted for traffic control for legacy applications. Second is a sidecar proxy that is a process that is injected and runs with your container or VM. So this provides end-to-end telemetry, but requires the management of an additional sidecar proxy binary and process with your microservice application. Third is to use a proxyless mesh where this is linked into your service and provided as part of the RPC library. And so this proxy list is best suited for very large microservices and provides the best latency, though since it is linked in with the application, it tends to have less functionality than a sidecar proxy due to concerns about application crashes. And for Google Cloud, these are all derived from the Envoy proxy, which is a modern, programmable, and extensible open source proxy. And for proxyless, we use gRPC. And in Google Cloud, we provide a fully managed service mesh called Traffic Director. This is fully integrated with our global load balancer, health checking, and auto-scaling, as described earlier, and this manages the service proxies for you. So Traffic Director allows you to benefit from the same load balancing features we just described for traffic coming from the public internet, to also the traffic between each of your microservices as part of your service mesh. And it's fully managed. So let's go through a quick example to show this. In this example, we use a sidecar proxy model with the Envoy proxy depicted here in the pink hexagons. So assume we have 3 microservices for the application called front end, shopping cart, and payment. And these are both deployed in the US and Asia regions. And each microservice uses an Envoy sidecar proxy that automatically is deployed and managed as part of the Traffic Director. So that pink hexagon is automatically deployed with your binary and managed by Google. And each microservice is provisioned in this example for 100 RPS in each region. So when traffic comes in from the public internet in the US, for example, the global load balancer will prefer to keep that traffic local and will route it through the microservices that are local, as shown here, if you have the available RPS capacity, which we do in this example. Okay, and this is using the same waterfall algorithm as described earlier. Similarly, for Asia, let's say, in this example, another 70 RPS is coming in through Asia. And again, the waterfall algorithm prefers to keep that traffic locally, which it can with the amount of available microservice compute capacity in each of these 3 microservices. Now, let's assume there's a failure to the shopping cart microservice in the US. In this situation, the load balancer sees a worldwide overflow scenario since there is more RPS coming out of the front-end services, a total of 120 RPS, than the available shopping cart capacity that is left, which is 100 RPS in Asia. So you see a 50 RPS out of the front end in the US and 70 out of the front end in Asia. But the only capacity left to serve for shopping cart is in Asia. Global Load Balancer then programs the sidecar proxies for both the US and Asia to send all that traffic to the shopping cart in Asia, as shown here. Now the question is, what to do with this 120 of RPS that's coming out of the shopping cart in Asia? So let's assume that we have auto-scaling. And so with auto-scaling, the load balancer will say to the shopping cart in Asia that I would like to send you 120 RPS. And so the autoscaler will kick in and autoscale the shopping cart in Asia and increase it to, let's say, 140 RPS with a little extra headroom due to how we set up our autoscaler. So now, what do we do with that extra load? Now, actually, we can, the load balancer will determine that we also want to load balance that 120 RPS coming out of that shopping cart in Asia across the available capacity in the payment microservices. So the load balancer knows that there is only 100 RPS available in the Asia payment service. And so it'll then load balance that 120 RPS coming out of the shopping cart across Asia and US. And it'll prefer to try to keep that traffic local. So it'll send 100 to the payment service in Asia and then 20 to the payment service in the US. Okay. Now, let's also assume that we have auto scaling set up for the payment service in Asia and US. And the load balancer will say to the autoscaler for the payment service in the Asia that I would prefer to send you 120 RPS because I want to keep that traffic local. So the next step is, you'll see, is this, which is the autoscaler in Asia will scale to 140 RPS, the 120 plus a little extra overhead. And then once that's available, the global load balancer will send all the traffic there. And so this will sort of be the steady state of the traffic flow until the US shopping cart region comes back online. So as you can see, the same global load balancing, health checking, and autoscaling being used for internet traffic is also used between microservices to continuously serve your traffic and keep it flowing. And this is provided as a fully managed service with the sidecar proxies being deployed and managed and programmed for you, even with autoscaling. So this slide shows how everything fits together. By providing a fully managed service mesh, we complete the end-to-end traffic management picture with the proxy management at the client, where you can use what's recently come about, which is the Envoy mobile for the proxy, to our Google Edge, and then all the way through your application's microservices as we just described. So this provides an end-to-end picture throughout your service and control for traffic. So the final topic I'd like to dive into is how to control traffic to achieve high availability for your application. So this is critical to ensure that the traffic to your service always stays under control. So your service doesn't get overloaded, fall over, and then everything goes down. So it's always important to have full visibility into your traffic using a service mesh across all your microservices as described. So at the highest point here, it's important to have automatic failover that is achieved from integrated load balancing with health checking that I've gone over in the talk. then it's critical to have a mitigation tool called draining in your toolbox to drain traffic away from a zone or region if you need to, and I'll get into that soon. This occurs if a region is partially healthy and the load balancer doesn't automatically kick in with the health checks and the health check manager that I described earlier. And finally, the last resort is rate limiting and circuit breaking to drop the traffic at the application or in the proxy or in the client. So I want to spend time on draining, and given how important it is and how much we use it at Google. So let's take our prior example with region A and region B with 10 requests per second coming into each region. Now let's assume there's a grave failure in region A, such that the service is not marked as unhealthy by our health check manager. So the load balancer does not know that region A should be taken out of service at this point. So it keeps on sending traffic there. And this can occur if you have a failure where, let's say, 10% of the traffic is failing, but not over 50% of the traffic is failing. So at this point, it can be useful to have an operator drain region A so that this tells the load balancer that that region or zone should not be serving any traffic. The load balancer will then click in with its waterfall algorithm and direct traffic to region B. And in running the service, you can see here that it's drained. Once that region is drained, that 10 RPS is redirected to region B. Okay, so I want to walk through sort of how does this work in the day of life for how we run Google. So draining is key, and it's actually more important than being able to quickly roll back recent changes, because you can instantly drain a region, whereas rollbacks potentially take longer. So let's assume that it's 3 a.m. Your site reliability engineer, SRE, gets paged that there's an issue with the service in a region or zone. And you discover this by using some telemetry with your dashboard that this microservice is having this issue. So with draining, you just drain the zone or region and you don't think about it. You just drain without actually questioning what to do next. So what this does, it allows you to quickly mitigate the issue. And because this instructs the global load balancer to redirect the traffic away so the traffic is sent to the next closest available region and spread around the rest of the regions or zones in the world. So you quickly mitigate the issue. You then spend time debugging what was going on in that region or zone that failed. And once you figured it out and you've actually fixed the issue, you then undrain the region or zone, and then load balancing kicks in and moves the traffic back. And this is really important for how we actually operate and mitigate issues every day at Google.
One quick question. So it sounds like it's sort of just table lookup, like knee jerk. Something's going on, drain that region. But what if it was like a time zone bug or something that affected multiple regions simultaneously? Is there some recipe there? Or are you running separate versions at different times, or how does that get mitigated?
You mean if there's like a larger than a single region outage, a multi-region outage? Yeah, the SRE, who's the expert on the service, will figure out the best course of mitigation. It might include draining some parts of some regions if it has enough capacity. One thing that we do, and it's a key part of building a resilient application, is making sure the changes you make are done incrementally. So anytime you roll out a change for production, it should be done a zone at a time, a region at a time, so that if there is an issue, the telemetry will quickly pick it up, and then if it's a code or a configuration change, you want to be able to roll that back quickly, or apply draining or something like this. So as anybody can tell you, running these services, anything that's a multi-regional outage is a big issue, because we really architect and run our services and partition how we actually do things so that the blast radius of an issue should be very small and typically contained within a zone.
Yeah, I love that point. I think it also just changes the way you think about developing the software. Like you develop it so that it can be released incrementally, which means planning, staging these versions in ways that you don't normally necessarily do. That's a really interesting point. Thanks.
Yeah, and just to add one little point on that, there are some things that actually do have to go quickly globally, though. Like these load balancing programming is done around the world quickly, within a few seconds. And so for that type of application, we do a lot of hardening and defense in depth so that those types of changes are in code that's basically been hardened over many years, as well as they are very limited to the types of changes that can actually get performed. So anything that actually can affect more than 2 regions at a time is under a heavy scrutiny, as well as a lot of defense in depth. Okay. Well, so now I'd like to wrap up. And in this talk, we went over the following key building blocks to achieve 5 nines in the cloud. This includes, keeping your data globally persistent in highly available global storage like Spanner, spreading your microservices across N+2 regions, using integrated global load balancing, health checking, auto scaling for both internet traffic and traffic between microservices, and provided by a fully managed service mesh like Traffic Director. And then using mechanisms like draining to have additional control over when things go wrong. So, and I just wanted to restate that in developing any application, one needs to assume anything that can go wrong will go wrong. So I can't emphasize enough that the application needs significant investment to achieve 5 nines along with the additional techniques we described in this talk. And listed here are some important ones, and the actual list is much longer. And I don't have time to go through all these since that would be a whole nother set of talks. But I did want to conclude with the following question, which is where do we go for achieving 5 nines? Businesses and consumers want and demand applications to be 5+ nines. But even with everything provided across all clouds today, this is not straightforward and it's hard to achieve. So we need to make it easier for developers and operators, to build and run 5 nines applications on lower available infrastructure, provide higher level building blocks like those described in this talk to try to abstract those problems away. And we need to look at how to better leverage multi-cloud for even higher availability. So all these are areas that need significantly more investment in the coming years to reach the availability goals that businesses, customers, and the world needs. So with that, I'd like to thank you for your time and attention, and thank you for having me. And let's go to any additional questions, I guess.
Thank you. Woo-hoo. All right, and we have a question here from Ed. Ed, do you want to speak live?
Yeah, sure. Hi, great to see you, Brad. What I said was I'd be interested in knowing the cause of 1 or 2 recent outages in an application that did all of these things. That is, it does happen, there's that 6th 9.
Yeah, let's see, what can I share? One thing to mention that I just described a second ago is when you do global changes, so some things, you do want to roll out things incrementally, right? But there are things that you really want to do globally and quickly, let's say like programming or global load balancer. That needs all this additional hardening and restriction on exactly what can be done. And so, there was an outage at some point recently where, there was additional, misconfiguration that could happen. And so, making sure that that's always hardened and restricted to just the bare minimal are types of things that the applications need to do to ensure that you don't have a multi-regional outage. And then that's why there's a lot of effort that the applications need to go through to do this sort of defense in depth and programming. So that's a recent one that's on my mind.
It looks like we also have a question from Curtis.
So what happens to flows that are ongoing when there are failures like this? Is there anything like, do those move over, or are they just disconnected and you hope the client reconnects and recreate whatever state they had?
Well, so the from the internet, the we use what's called the Anycast IP. So we actually have a solution called maglev that's under the cover that keeps the connections established. And there's a paper actually published on it a few years ago. I can't remember what year, but you definitely want to know more about it. We have a whole paper describing how maglev works to keep those connections connected in conjunction with the global load balancer.
Cool. Thank
you. That's MAG LEB, maglev.
And I have what could be a related question. So a lot of your examples were related to applications with transactions on data, on storage, right? So how do you think about applications like, Google Meets or Zoom, where have, harder real-time requirements and bandwidth availability, where the notion of working, not working is much fuzzier, right? So is it exactly the same set of microservice infrastructure, web of microservice infrastructures that talk to each other and keep, those live streams flowing, or is it a completely separate, set of microservice infrastructure for live applications? Yeah.
Yeah. So basically, what I described here is exactly how we keep the Google applications up and running. Of course, there's additional application logic that they do on top to do the defensive depth and degradation. So, for example, if something was not available from a backend service for a search, for example, it may return a more degraded result. But the key is to always keep on serving results, even if something that's a dependency you have might fail. So there's that type of defense in depth that's done at the application layer. But all the things we talked about here in terms of running across multiple regions, doing the load balancing, doing the health checking, that's all leveraged to keep those our Google applications running.
I see. Oh, sorry, I guess I wasn't clear with my question. Now, what I was asking about is for applications like video conferencing, right, where you have a continuous stream between you go stream to the cloud and you might distribute to multiple clients. Are those applications that have, let's say, more strict bandwidth and latency requirements treated very differently than other applications like email or, that's what I was thinking about. Yeah. Are those considered, very different classes of applications, or they're the same?
I haven't been deeply involved in the media applications. Like when YouTube, as I understand, as YouTube streams come in and they need to be streamed out, for example, they go through highly available encoding services, which then get distributed with our CDN technology. So, the CDN that we have is, as you saw on that one slide, is massively scalable. It serves YouTube. As you can imagine, the amount of terabits per second that serves. And, it's in 3,000 plus locations. So, as long as we have the highly scalable, compute and encoding, et cetera, behind for like our media, like video chat or video, serving, the CDN is what then actually gets it out everywhere around the world in a reliable manner.
Thank you. More questions from the audience. Otherwise, I have one more, but we want to hear from the audience. So
maybe while folks are thinking, I just kind of am still on this theme. All of the work here is somebody mentioned in the chat. It's great, right? It's all this stuff that allows me to just click and have an application work. And so in some sense, it's creating this abstraction for my application that I have, a global computer that's always there. But of course, like the typical question is like that abstraction comes at some cost. So I'm wondering if there's any sort of back pressure or feedback to the application about when things are tight. I don't know if you could reflect this somehow, maybe with like pricing to customers or something, but if I have a huge app, I can choose whether or not to send out notifications or reminders that might cause traffic spikes. And if there's something else going on in the world, maybe I'll hold off on that. Is there any kind of feedback or back pressure that allows application level decisions to help keep things running smoothly across the whole world?
That's a good question. For example, if you're using the service mesh and telemetry, you can actually hook telemetry into your application logic to decide, how much capacity do I have based upon how much capacity I want to spend. A big, topic I didn't get into that is a trade-off in cloud is how much do you spend on reliability, right? Because you can actually run across all regions, or you can run in a single region or a single zone. But as you run more and more, even though we do allow you to shrink really small and scale up, the cost of that increases. And so you see a lot of customers go through this trade-off. One is they're going through a journey from maybe running in a given data center to the cloud and then going multi-regional. But even then, there's this trade-off between how redundant do you run? And so by getting back to your question, you can hook into telemetry to actually guide what you want to do there, or if you actually want to add more scale. But the great thing about it is if you can afford the additional capacity, you can let the load balancer direct the traffic and the autoscaler kick in and autoscale to meet the traffic spikes that you have. But there is a trade-off there that some people are concerned about in terms of cost versus the scale that they actually are consuming.
What do you think are topics that make sense to do research on in academia? Of course, nobody can compete with Google in general cloud infrastructure, but I wonder if there are specific questions that you wish an academic could spend time on.
Well, that's why I threw this last one up in this last slide, is I actually do think that this is, we've talked about in the Google Cloud for a while, the notion of having a self-driving cloud, just like you have a self-driving car. And I don't know if you've seen the videos from Google about our self-driving cars, but very we pivoted at one point to basically threw out the steering wheel, because the steering wheel is just too much of a temptation for people to have too much confidence. And I think that's a good analogy here in that you need to be automated, fully automated. If you think you can rely on humans to come in and mitigate all the issues, you just can't get to 5 nines. But I think pushing towards how do we actually provide higher level abstractions, how we do multi-cloud. I think there's lots of interesting areas that we need to invest in industry and potentially in academic research.
Great. With that, well, thank you again, Brad. It's really a pleasure to have you here, and awesome again that we can click around and stuff actually works in the cloud. So it's great to take a peek on how things actually work here. Thank you.